Welcome to part 5 of neural networks, backpropagation. This is one of the most critical aspects of neural networks as we try to update our weights and biases when we figure out what our loss is, or what the difference between the network output value and the real output value is. Backpropagation allows us to minimize that loss and achieve the maximum accuracy possible. So let's define our variables. L is the last layer, and the layers before are notated as L-1, L-2, all the way to some L-n. Focusing on the last two layers, let's define Z equals Wx plus B. When we apply an activation function, A equals sigmoid of Z, this means we have Z to the L, so the Z in the last layer equals W to the L, the weight of the last layer, times A to the L-1, the activation function of the previous layer, plus B to the L, biases of the last layer. And using this, we can also conclude that A to the L equals sigmoid of Z to the L, using this definition of A, and the cost function, the cost of whatever those variables are, equals A to the L minus Y, all of its square. If you remember, we square the cost function to punish large errors and to keep it positive. Partial derivatives. So we want to understand how sensitive the loss or cost function to changes in W. Loss and cost functions refer to the same thing. It's just a different way of saying it. So how do we understand the sensitivity of this loss function to how W changes? We can get these formulas for the weights and biases using the relationships we know with the chain rule. For those taking calculus, chain rule is the stuff of nightmares. For those not taking calculus, you will eventually encounter this nightmare at some point in your life or the other. For now, you don't need to exactly understand what the chain rule is, but just get the main ideas. What the main idea is that we can use the derivative or the gradient to go back through the network and adjust the weights and biases to minimize error. Remember, from our gradient descent video, we explained how we decrease the slope gradually until we get it to 0. The derivative is just the slope. You can think of it like that. And we use this slope or gradient to go back through our neural network and adjust weights and biases to make the error value as small as possible. So these formulas might look pretty complicated, but they're simply saying how we get the parts of the cost function, and we relate that with the derivative of the cost function. So it's saying that the derivative of the cost function in respect to the biases of the last layer is equal to the derivative of Z to the last in the last layer to the respect of the biases of the last layer, A to the last layer, and the cost function. So if you see, everything cancels out. Like this Z to the L term cancels out with this term, this A to the L term cancels out with this term, and this C sub 0 and over B to the L is all we have, which is equal to the term on the left. So you don't really need to understand this. It might be a little complicated, but just understand the main idea. Next is, we'll just define what the Hadamard product is, because it'll appear in some equations and we don't want to get lost. So this dot symbol denotes a Hadamard product. It's simply just element by element multiplication, where the matrices are the exact same size. For example, in the picture on the left, we have a matrix of 1, 2 times the Hadamard product of 3, 4. What we do is just multiply the two top terms and the two bottom terms, and we get a matrix of 3, 8. This matches up for the weights and biases in our neural network. Again, This might be a little complicated, but you just might want to know it in case you get confused in some of the equations. Definitely you can do research on your own, denoting probably a better explanation of the Hadamard product and how that applies to neural networks. I highly recommend StatQuest. They have really good explanations. So let's actually get down to business. How do we train neural networks and update these weights and biases? I know I've been harping on this for a while, but this is the main stuff. Step 1. We use the input x to set the activation function a for the input layer. Remember, z as the tensor input equals w times x plus b, where w is the weights and b are the biases. And we defined a as the activation function, where z is the input of the activation function. Now that's represented by a sigmoid. This a, the output, feeds into the next layer, and so on. Remember, if you imagine a neural network, all the outputs of one layer are the inputs of the next layer, and so on and so on and so on until the output layer. Step 2. For each layer, we need to compute z of the last layer and a of the last layer. So using the notation and variables we defined previously, z to the L equals the weights of the last layer times a to the previous layer plus b to the L. And a to the L equals the sigmoid of z to the L. So we've defined z to the L and a to the L. Next, we compute the error vector. Now, this also looks a little complicated, but all it's saying is the rate of change of C with respect to the output activations. So how is the cost function changing? Basically the derivative of the cost function with respect to the activation function, which would be the sigmoid function. That's denoted here. So the vector is represented by an upside down triangle. The vector of C is the Hadamard product is taken of the vector of C and the derivative of the sigmoid function. The apostrophe next to the sigmoid represents the derivative. And we also define that how C changes is defined as a to the L minus y. This looks pretty complicated, but just understand the main ideas. Step 4. We backpropagate the error. This is the generalized error for any layer L. Now, L doesn't have to be the last layer, it could be the third layer, it could be the fifth layer, any layer. So this formula represents the error delta of that layer. It's saying what the error is that we have to update the weights and biases for. The formula is saying that delta to capital L equals the transpose of the weight matrix, W to the L plus 1 all to the T. The transpose weight matrix is basically moving the error backward through the network. This gives us some sort of measure of the error at the output of the out layer. So we know how much to change our weights because we have a measure of the error at this specific layer. Then we take the Hadamard product of the derivative of the sigmoid function at that input z to the L. This simply moves the error backward to the activation function in layer L, giving us this error delta to the L in the weighted input to layer L. This Greek letter here is simply delta. So intuitively, this makes sense. We're getting the difference from the loss or cost function. We're backpropagating it, so we're moving this error backwards, this difference backwards from the output of the neural network all the way to the input closer and closer. And we stopped at some layer L, which we want to fix the weights and biases for. And at that layer, we find a measure of this error. Now we know what this measure is, so we can adjust these weights and biases accordingly because we know what the measure of the error is at this specific layer. So this Backpropagation is one of the most complicated concepts in neural networks, so I definitely recommend doing some research on your own. You'll also learn about, you'll also see how to do backpropagation in the next video, where we'll discuss, we'll show you how to implement neural networks into code and how all of these concepts look at a concrete level. So, so we'll see you guys in the next video, where we'll be talking about the implementation of neural networks, and you can follow along if you want to as well. See you guys there.